In the previous video, we looked at using the method of Lagrange multipliers to solve extrema problems for a function of two variables with a constraint on a curve of with two variables. In this video, we're going to start with an example with a function of three variables and want to find the global extrema of that subject to a constraint given by a function of three variables. And we're going to see that it extends naturally in sort of the obvious way. So if I want to find the global extrema of a function f of x, y, z, so a function of three variables now, subject to the constraint g of x, y, z equals k, right, for some constant k. This can be found by solving a system. And turns out it's the exact same system as it was for two variables. The gradient of f of x, y, z equals some constant lambda times the gradient g of x, y, z. Okay. And, of course, the constraint equation itself, g of x, y, z equals k. Okay. So this is actually a system of four equations. That first vector equation, we want to set each of the three components of the vectors equal to each other. They're the partials with respect to x, y, and z respectively. Now, the reason that this works is exactly the same as in the two variable case. We just don't have a nice picture to draw because these are now functions of three variables, so the domain are regions in 3 space, and the function values are actually in a fourth dimension that we can't draw or realize in any kind of visual way. And so we have to just kind of take the algebraic the approach that the algebra works on it, and it does. If you're interested, you can verify that in pretty much any calculus book. Most of them will have some verification of this formula. But we want to really just use this for this kind of a class, so that's what we're going to do. This, of course, even extends beyond this if we wanted to do functions of 4 variables or 5 variables or however many we wanted to. The exact same system works, it's just the system gets more equations and therefore more complicated. So let's look at an example. So we have a delivery service that will only deliver a package whose length plus girth is no longer than 84 inches. So in this case, length means the length of the longest side of the box, and girth is the cross-section, the perimeter of the cross-section orthogonal to that length. Okay? And so our question here are what dimensions maximize the volume of such a box? Right? So if I take a box looks something like this, we can label the three dimensions x, y, and z. Right, so what we want to do here is we want to find the maximum value of the function f of x, y, z equals x, y, z, the product. That's the volume of this particular box. So we want to maximize this subject to a constraint right? And that constraint is that the length, all right, the way that I've drawn the box, it looks like x is my largest side, so I'm going to call x my length. And then the girth is the perimeter of the cross-section, so it would be this perimeter here around the edge. And so that would be 2y plus 2z. And so our function g, our constraint function, is going to be x plus 2y plus 2z, and we want that to equal 84. Right? Logically, if it is possible the length plus the girth could be shorter than 84, But the maximum volume is going to occur when that length plus girth is as large as possible. If we had that number being 70, we could make one of the dimensions of the box longer and therefore give a larger volume. So the largest volume is going to occur when this length plus girth equals 84. Right? So these are our functions. And so we want to apply Lagrange multipliers to this function f subject to this constraint g. Right, so if we compute our gradient vectors, g of f of x, y, z, partial with respect to x will be yz, the partial with respect to y will be xz, and the partial with respect to z will be xy. And the gradient vector with respect to g, the partial with respect to x is simply 1, with respect to y will be 2, and with respect to z will be 2. So we have a constant vector here. So the system of equations that we're going to set up is that the gradient of f x, y, z is going to equal the constant lambda times the gradient of g of x, y, z. And the equation x plus 2y plus 2z equals 84. Right, so this will be our system. So we'll set each of the coordinates of our vector, or the components of our vector equation equal to each other. We'll have a system of 4 equations and then attempt to solve. So when we set those components equal to each other, we're going to get yz equals lambda times 1. Xz is going to equal lambda times 2. And xy is going to equal lambda times 2 as well. And we have this constraint equation, x plus 2y plus 2z equals 84. Okay, so just like before, I'm going to label these equations 1, 2, 3, and 4, just to make it clear what equation we're working with and what we're doing. So the first thing I'm going to point out here is that we're going to ignore all solutions that work with 0. Right? Remember the previous example in the last video, I pointed out that we have to consider things where we want to make sure not to throw out any solutions by just assuming something is non-zero. But in this case, I actually can assume x, y, and z are all non-zero because we're looking for the maximum volume. And if one of the 3 variables is equal to 0, then the volume is going to be equal to 0, which would not be our maximum volume. So just as a comment that I'll make up front, I'm going to ignore all solutions of 0 for this particular problem. But that is simply because of the context of the problem. We know 0 is not going to be a solution, so there's no need to consider it. Right? And so there's a variety of ways we can go about solving this, but one of the things that strikes me about this equation, or about this system, is that equations 2 and 3 have the same right-hand side. They're both equal to 2 lambda. And so if that's the case, then the left-hand sides of those equations must be equal, and so we have xz equals xy. And now there's 2 possible ways this equation could be true. The first is that we could have x equal to 0, but we just said we're going to ignore solutions of 0, so I'm going to assume x is not 0. And if x is not 0, then I can divide both sides by x, and I'm left with z equals y. And so we have this, this takeaway from combining equations 2 and 3, and that y and z have to equal each other. Right? All right, so now if I go back, we'll use this fact in a moment. If I go back and look at equation 1, I can multiply equation 1 by 2. So I have 2yz equals 2 times lambda. And now using equation 2 as well, I know 2 lambda is equal to xz. All right, so this now also through, I'm going to label 2 over here. I also use 2 there for the second equality. So 2yz equals xz, and again, we're assuming z is not 0, so we can divide by both of those. And so we see that 2y has to equal x. Right? And so now we sort of have everything we need. We have x, we know how to write, we know how to write z in terms of y. We know how to write x in terms of y, and of course y is equal to itself. And so we can take all of these values and substitute them into the fourth equation. Right? And so our fourth equation, we have x, which is we just showed was equal to 2y, right, plus 2y. And then we want plus 2z, but we showed z was equal to y, so this is also equal to 2y. And this has to equal 84. Right? All right, so this means we want 6y to equal 84. And therefore, y is going to be 10 plus 4 is 14. So the only solution to our problem must have a y value of 16. Oh, I'm sorry, 14. Right? So we must have y equal 14. I know that z is equal to y, so z must equal 14. And I know x is equal to 2y, so x must be 28. Right? And so this is the only value that we get by solving our system of equations. And so because it's the only system, these must be the dimensions of the maximum volume. So we must have a dimension of the length of 28 inches and then a width and height of 14 inches. It's the only possible solution to our problem, and therefore it is the solution that we want. Right, so let's take a look at another example. So let's say we want to find the point on the plane negative 2x minus 6y plus 4z equal to 8 closest to the point 1, negative 2, 3. All right, so we have this plane in 3 space, and we have this point that's not in the plane, and we want to find that point that is nearest the point subject to being on the plane. Okay. So we're going to start here. We're going to let x, y, z be a point on our plane. So it's just an arbitrary point on our given plane. And what we want to do in this problem is we want to minimize the distance from x, y, z to 1, negative 2, 3, subject to the constraint that our point satisfies the equation of the plane. Right? And so our function here the thing we want to minimize is this distance, and we know how to compute the distance from one point to another. We have the distance formula. So the distance is going to be the square root of x minus 1 quantity squared plus y plus 2 quantity squared plus z minus 3 quantity squared. Right, so this is going to be the function that we want to minimize. And this can be actually a little bit problematic because we're going to have to take the gradient of this, and that's going to be a little difficult to deal with. And so one observation we should make in this particular case is that the same point that minimizes this particular function will also minimize the function f of x, y, z equals the square of this distance, x minus 1 squared plus y plus 2 squared plus z minus 3 squared. Right? So because we know the distance is a positive number, we're only looking for that positive square root value. The point that minimizes the square root function will also minimize the radicand function, the thing inside the square root. And that's going to be much easier to compute. And so this is the function that we're actually going to use to minimize. And the function g is going to be our equation of the plane, or that left side of the equation of a plane. So negative 2xy, or negative 2x minus 6y plus 4z. Right? And so here we have everything we need to be able to solve this problem. And so the first thing we need to do is find the gradient of f and the gradient of g. Right, so the gradient of f is going to be the vector 2 times quantity x minus 1, 2 times the quantity y plus 2, and 2 times the quantity z minus 3. Right, so there's our gradient of f, and the gradient of g will be the coefficients of the variables, so negative 2, negative 6, and 4. Right. And so the system that we're going to solve, we'll just set these components equal to each other. We're going to have 2 times x minus 1 equals negative 2 lambda. We're going to have 2 times y plus 2 equals negative 6 lambda. And 2 times z minus 3 equals 4 lambda. Right? Subject to this constraint, negative 2x minus 6y plus 4z equals 8. So this is the system of equations that we need to solve in order to find the point closest to, or the point on the plane closest to the point 1, negative 2, 3. We want to minimize that distance function. And so in this case, the strategies we used on the previous two examples really don't apply here. We don't have two of the right-hand sides being equal to each other. We don't see a nice way to set two variables equal to each other or anything like that. The thing that we observe about this particular system is that the first three equations each involve only one variable. So the first equation only involves x, the second only involves y, and the third one only involves z. There's no interdependence between the three variables in those equations. And so what this allows us to do is to solve for x, y, and z individually in terms of lambda. And once we have that, we can substitute all of those values into the fourth equation and then determine what value lambda has to have, and then go back and use the value of lambda to compute x, y, and z. Right? And so we're just going to do each of these three equations separately. The algebra is very simple, but if we get rid of the 2, if we divide both sides by 2, I get x minus 1 equals negative lambda. And therefore, x is going to be 1 minus lambda. So there's x in terms of lambda. The second equation, if I divide by 2, we get y plus 2 equals negative 3 lambda. And so I subtract 2 and get y equals negative 2 minus 3 lambda. And the third equation, I get z minus 3 equals 2 lambda. And so z is going to equal 3 plus 2 lambda. Right? And so now we're going to take all three of these values and we're going to substitute them into our equation here. Right? And so when we do that, right, we get negative 2 times 1 minus lambda minus 6 times negative 2 minus 3 lambda plus 4 times 3 plus 2 lambda, and that all has to equal 8. So when we distribute all the terms on the left-hand side and we combine all those like terms, what we will end up with is 28 lambda plus 22 equals 8, which means we have 28 lambda equals negative 14, and therefore lambda has to equal 1/2. I'm sorry, negative 1/2. Okay. All right, so if lambda is negative 1/2, we can then take lambda, substitute them back into the three equations in the red box, and have the point that we need. All right, so our point, we have x being 1 minus lambda, so that would be 1 plus 1/2, so 3/2. We have y is negative 2 minus 3 times negative 1/2. So negative 2 plus 3/2, that will be negative 1/2. And z will be 3 plus 2 times negative 1/2, which will be 3 minus 1, which is 2. And so the point on the given plane that is closest to the given point has coordinates 3/2, negative 1/2, and 2. And so you can check if you want that point is on the plane, and you can find the distance if you wanted to, although we don't necessarily have to in this case. We know this is the only point that is going to work. And so this strategy here is just, again, another strategy for solving a system with Lagrange multipliers, but it really only works well when each of the equations from the setting the gradients equal to each other involve only one variable each. Right? And notice that in the other examples, I didn't explicitly point this out, but in the previous two examples, in either of those cases, neither of them did we actually find the value of lambda. Right? We don't actually care. It's just the nice thing about it is that it's a nice tool to help us solve for our solution. In the one example, we had one case where we knew lambda was 0, but in the other case, we didn't really care what lambda was. And in the second example we had no interest at all. We just used lambda to find relationships between x, y, and z. Right? And so we don't have to find a value of lambda, although in this case it actually is the best way to go about it. So it is one option.